Everyone. Thank you for having me here. You have a lovely facility. I do have to warn you, I am not an observational astronomer by training. I don't know much about what's in the sky or instruments. I just sort of started getting into that this summer while actually giving tours with some of you at MEES. So I wanted to give this talk on observing dark matter, which is the research that I do as a PhD student. The observing part here is a lie. We can't observe dark matter. So what I really do is observe the effects of dark matter on visible matter, and I try to understand where this dark matter is inside galaxies. So first I'll tell you a little bit about the first prediction of dark matter, zooming out from galaxies to galaxy clusters. So here I have a picture of the Coma cluster. So this is a cluster of over 1,000 galaxies that are gravitationally bound together. And in 1933, Fritz Zwicky, who was a Swiss astronomer, wanted to figure out how much mass was in this cluster. So he used the virial theorem, which says that there's a relationship between the gravitational potential of this cluster, so how much mass it has, and how fast the galaxies in this cluster are moving. So he measured the velocities of these galaxies, and he basically added up all of the stars that you can see in these galaxies and estimated the gas from these galaxies. And he realized that the total mass of the Coma cluster is 400 times the mass that you get just by adding up everything you can see. So that's a huge discrepancy. And he coined the term dark matter for the mass that you can't see in this cluster. So this estimate was actually very wrong. It's actually much closer to the total mass is 30 times the visible mass, which is still a very significant discrepancy between what you see and what's actually there. So fast forward about 40 years later, in the 1970s, we started looking into a dark matter inside galaxies. So we're on a much smaller scale. So in the 1970s, Vera Rubin, an American astronomer, used a technique called long slit spectroscopy to measure the rotation of galaxies. So spiral galaxies are supported against gravitational collapse by their rotation. So how fast they're rotating should correspond to how much mass is in those galaxies. So what long slit spectroscopy does is taking measurements or measuring spectra across the major axis of a galaxy. So for this galaxy, which is one of the galaxies from her sample, it's sort of like taking spectra at a bunch of points along this line. So what does this actually look like? So here is a galaxy that I've used in my research. So we take a measurement at the center of this galaxy, and this is what the spectra looks like. So along this horizontal axis is wavelength. And what we do is we look for a feature that we expect to find everywhere in spiral galaxies. That prominent emission line right in the middle, that's the H alpha emission line. And that's the line that Vera Rubin used in her studies to measure rotation. So here I've just zoomed in to that line. That the tallest hump here is that H alpha line. And we have a location for this in wavelength. So then we take another measurement on one side of the galaxy, and we still see the same H alpha line, but it's shifted a little bit to the left here. It's a little hard to see, but if we take another measurement on the right side of the galaxy, now you can see a little bit better compared to that vertical line. This H alpha line is now shifted to the right. So this can tell us about the rotation in these galaxies. So the way we get to rotation from that spectra is by calculating redshift. So when an object is moving away from us, its spectrum is going to be shifted towards the redder side of the wavelength spectrum. And then if it's moving towards us, it's going to be shifted towards the blue. So in the center here, I have an example rest frame wavelength, rest frame spectrum. So we have all of these prominent features, and you can see when it's redshifted, all of those features just shift to the right. And when it's blue shifted, they all shift to the left. So here is our center of the galaxy spectrum again. And we know what the rest frame wavelength of H alpha is because we've measured it here on Earth. So if that galaxy was right where we are right now, that line would be at 6,564 angstroms, which is 656 nanometers. And we can calculate essentially how fast this galaxy is moving relative to us based on the difference between where that line is appearing in the spectrum and where it should be if it was right here, which is at 656 nanometers. And so we do the same thing. We can treat that center point as sort of our zero for our galaxy, and we can calculate the velocities relative to that zero for the other 2 points. And that tells us how fast one side is moving towards us and how fast the other side is moving away, so how fast that galaxy is rotating. So this is what Vera Rubin did with a sample of around 20 galaxies, just along the major axes of all of these galaxies. So back to that example galaxy I showed. So this is her velocity measurements from that galaxy. So you can see the zero line in the middle, that's the center of the galaxy. And then on the left side of the galaxy, you have much lower velocities, and on the right side, you have much higher velocities. So the way I like to look at this is as a rotation curve. So the bottom curve of these two here is the one corresponding to this galaxy. This shows the velocity as you get further away from the center of the galaxy. So you can see a curve that rises up to a certain point and then it becomes flat. So this is something that appeared in every rotation curve in Vera Rubin's sample, which was a little bit strange. Because if we look at a galaxy, the brightest part of the galaxy is the center, and then it starts to get fainter as you get further out. So what we expect is if that's all of the mass in a galaxy, the rotation should start to decrease as we get further away. The velocity should be lower, but instead we see this flat rotation curve in every spiral galaxy. So the bottom curve there, that's what we expect from just stars and gas. And then this flat rotation curve is what we keep observing. So this difference is what we attribute to the presence of dark matter. So this was the second sort of major observation that gave us evidence for the existence of dark matter, now on a smaller scale inside galaxies themselves. So my research focuses on trying to understand how much dark matter is inside galaxies. So from this rotation curve that we observe, we can understand how much total mass a galaxy has. But to understand the dark matter, you have to take all of the parts of the galaxy that you can see, add those up, and subtract it from the total mass. So I focus on trying to make sure we're accurately accounting for all of those visible mass pieces. So spiral galaxies have a bunch of these components in common. They consist of this bright stellar disk and bulge. This is where most of the stars in the galaxy are. This also contains the majority of the gas, which is primarily neutral hydrogen, molecular hydrogen, and helium. And then everything heavier than helium exists in very small amounts. Astronomers like to call those metals. So anything, even sodium, we'd consider a metal here. And then all of this lives inside a dark matter halo. So for my research, I use data from the Sloan Digital Sky Survey, mapping nearby galaxies at Apache Point Observatory, or MONGA. This is the instrument on the top right. So this instrument uses integral field spectroscopy. So instead of that line of measurements along the galaxy, instead now we can take measurements all over the face of a galaxy. So this hexagon that you see on the bottom, that's called the integral field unit. And each of those circles is a fiber that is pointed at that galaxy. So this survey has been, it started in 2014 and ended in 2020. So it had a 6-year run. And its depth went up to a redshift of 0.03, which is about 126 megaparsecs or 400 million light years. still considered the very local universe in my research. And over that 6-year period, it observed 10,000 galaxies. About 5,500 of those are spiral galaxies that I use in my research. So on the top right, you can see one of the galaxies from manga. That purple hexagon is the outline of where that integral field unit corresponds to on that galaxy. And on the bottom, each of those circles is where one of those fibers is pointing at on this galaxy. So this results in a 3D map of each galaxy, where 2 dimensions are the space or spatial dimensions, and then the 3rd dimension is actually a wavelength, because you get a spectrum from every single one of these fibers. So this is my example galaxy, affectionately named 89979102. And here is a wavelength slice from this galaxy. So you can see the horizontal and vertical dimensions, and then the color is actually the flux of H alpha. So I chose an H alpha slice to show here. So I have spectra at all of these different pixels on this galaxy, and I can turn these spectra using the position of the H alpha line into velocities to figure out the rotation of these galaxies. So what that gives me is a velocity map for this galaxy. So here the red shows motion away from us and the blue shows motion towards us. What I've done is I've subtracted off the velocity at the very center of this galaxy, so you can just look at it like we're right in the middle of this galaxy. And this galaxy is rotating in this direction. So what I do with this map is I fit a model of a velocity map that describes that rotation curve that we saw that rises up to a certain point and then it becomes flat. So this is what my model looks like. And I'm doing this for all of the 5,500 galaxies in my sample. So here's the same map, but I've turned it into a 1D rotation curve instead. So all of the black points are the data that I'm getting from manga on the velocity, and that blue line is my model. So you can see that it's a rotation curve that rises up to a certain point and then it becomes flat. So I have this rotation curve, and now I can use this to calculate the total mass of my galaxy using this equation here. So this is just using Newton's laws. All I need is the velocity at any point, the distance of that point from the center of the galaxy, and the gravitational constant, which I know, and I can calculate the mass of this galaxy. So now that I have the total mass, I have to get all of my visible mass components so that I can subtract them off and figure out how much dark matter there is. The first one I start with is the easiest, is the stellar mass. This is a stellar mass map for this galaxy. So you can see the center of the galaxy has a much higher concentration of stars than the outskirts of the galaxy. And I fit this to a distribution for a disk and a bulge, which is what we see in spiral galaxies. So if I were to get a rotation curve from just this stellar mass, that would look like this. So you see a rotation curve that rises and then it starts falling instead of becoming flat. So for all of the galaxies in my sample, the left side is the total mass rotation curves that I got from my H alpha data. And the right side is from the stellar mass distributions. So you can see this pattern of rotation curves that rise and become flat when you consider the total mass. But then when you look at the stellar mass, they start falling off. And what this tells me is that the stellar mass is not enough to explain the rotation of these galaxies. There's something more than stellar mass here. Yeah.
Is the rotation uniform?
Not necessarily, but I can approximate it to be uniform because I'm using this model fitting. It makes it a little bit simpler. So you can see, just go back so I can show you. So at any radius, there's still like a spread of points, basically. So there are points with different velocities.
So galaxies turn like a giant.
Yes.
Were the 5,500 galaxies selected because they are oriented in a way that makes them easier to get data from?
So I first I selected spiral galaxies because those are the rotating ones. And then I did make a cut on inclination because if a galaxy is totally face on, it's rotating this way and you don't get a difference in motion because you're looking at the line of sight. So I made a 5-degree cut so I have enough of an angle where there's some line of sight velocity basically. So the next component is gas. This was pretty simple. It didn't require a lot of work for me. I used an H1 follow-up survey for manga to get my H1 masses. For molecular hydrogen, it's actually very hard to detect molecular hydrogen because of its structure. So instead, what we typically do is use another molecular gas, so carbon monoxide in this case, which has a very tight correlation with the amount of molecular hydrogen. And we use that to estimate how much H2 there is. And then helium, we use a simple estimate saying it's about 25% of the total gas in a galaxy. So the other thing I had to consider is the metallicity, which is how much of the gas in a galaxy is metals or elements heavier than helium. For metallicity, we typically measure the amount of oxygen relative to the amount of hydrogen in a galaxy. That's a good tracer for how much heavier elements there are. So here's a metallicity map. So the purple regions are the regions with less oxygen relative to hydrogen. And then the yellow regions are the ones with a little bit more. You can see it's pretty patchy. So I use this to estimate how much more of the gas in the galaxy is just heavier elements. So just a summary of all of the visible mass components that I've collected. I've gotten my stellar mass from that stellar mass distribution map. I got gas from a couple of different surveys and making a mass estimate. And then I've calculated the amount of heavier elements using the metallicity of galaxies. So this is just all of the components that I've put into the visible mass in my studies. So I wanted to show what I found about just the contributions to the visible mass first. The first thing that I found is that faint galaxies have a lot of gas in them. So this bottom purple line here, that shows the fraction of visible mass that's just stars in a galaxy. And the left side of this is fainter galaxies, and the right side is brighter galaxies. And then this blue line here, that shows stars plus gas. So this means that the difference between these two lines is how much gas is in a galaxy. And you can see on the left side of this, where the faint galaxies are, there is way more gas relative to the amount of stars in these galaxies. So one thing that's really important about this is that most previous studies that have tried to understand how much dark matter is in galaxies have only used stars in their calculations, or they've used stars in H1. And when you do that, you're going to overestimate the amount of dark matter that's there. So my study focused on making sure that we really understood how much H2 there was and how much helium was and adding that into the mix. So if you don't include that, you're losing almost 15% of the visible mass. And then all of the heavier elements, that only contributes about 1%. So it's okay if we're not keeping that in the mix here. Yes?
So faint galaxy.
A faint galaxy.
Faint.
So I'm sorry, what?
It's faint. Yeah, what is that?
A faint one?
Yeah.
So in this case, faint galaxies are mostly galaxies that are earlier in their evolution. So they haven't converted their gas into stars yet. Yeah. So this is absolute magnitude, so it's not relative to distance in any way.
What's
Those are the magnitudes, actually. So those are absolute magnitudes. So astronomers have a fun system where it goes in the wrong direction.
advanced?
Yeah, so -13 is a very, very faint galaxy, and negative 22 is a really bright galaxy here, which doesn't make a lot of sense. So the next thing I looked at was the ratio of visible to total mass. So that horizontal line there at 1, that is the total mass of these galaxies. And all of these points here just show different estimates of the visible mass. So on the left side is fainter galaxies, and on the right side is brighter galaxies. So what I found here is that on the faint end of galaxies, there seems to be less visible matter compared with their total mass, which means they maybe have more dark matter inside them than their brighter counterparts. So what I found is that within the visible extent, 40 to 60% of these galaxies, the mass of these galaxies is dark matter, which is pretty exciting. So this is what I've been doing for the last couple of years, this rotation curve study. And it does a good job of telling us how much dark matter there probably is inside galaxies, but it doesn't tell us much about how that dark matter is actually distributed. So in order to understand that, we can't use rotation curves, but the most popular method for studying that is using gravitational lensing. So gravitational lensing is this phenomenon that happens when you have a very heavy object, very massive object like a galaxy cluster. So you have thousands of galaxies, and then you have a small bright object behind it, like a galaxy. And the light emanating from that galaxy gets bent around the cluster towards us. And what happens is it magnifies this galaxy, and it also produces multiple images of it. So you'll see multiple images of the same galaxy on either side of a cluster when lensing is happening. So this lensing was predicted by Einstein in his theory of general relativity, but Zwicky actually proposed using clusters as lenses in 1937, and we didn't actually follow up on that until like 50 years later. So here is an example of a galaxy cluster acting as a lens. So you can see these sort of circular patterns around the cluster. Those are all galaxies that are being warped by this lensing effect. And if you're really lucky and your lens and your lensed object are in a good position, you end up with an Einstein ring, which is that full image that is a complete circle around your lens. And you don't need a galaxy cluster to have lensing. This is actually just an elliptical galaxy that's acting as the lens here. So one of the reasons this lensing is useful in astronomy is if you have a galaxy that's faint behind your lens, it's going to magnify it, and you can do a lot of interesting studies on it that you wouldn't otherwise get to do because it's too far away. So lensing can also show the distribution of dark matter inside these clusters. So on the left, I have a picture of a cluster that's acting as a lens here. And it's producing lots of images of the galaxies behind it. And what the scientists have done is they've, based on these images, mapped out what the distribution of mass should be in this cluster. So on the right side, that's what they predict is the distribution of mass based on these images. So all of the light blue, that's where the dark matter is. So what's kind of interesting here is there's this weird ring structure. We have no idea why that's there. I think it's pretty cool. I think some people suggest that it's because of a cluster of mergers happening, but there's no confirmation on that. So now we kind of understand, or we have ways to find how dark matter is distributed. You might be wondering, why don't we just use lensing? Why use rotation curves at all if we're not going to understand the distribution? For lensing to be used effectively here, the cluster has to be fairly close to us. So we have very few lenses that we can use in that way. And for smaller objects to act as lenses, so elliptical galaxies, you have to have a galaxy behind it lined up really well to be used as a lens. And we're not that lucky. We don't get those that often. So that's the downside of that. We have a little bit more statistical power if we're using rotation curves to study dark matter. So now I'll talk a little bit about dark matter candidates. So what is dark matter actually? Right now, our understanding of it is basically just the properties we think it has. It does not interact with the electromagnetic force, so it's not producing light. That's the one thing that we definitely know about it. Otherwise, we would see it. It has mass because the only effect we see is through gravity and how it acts on matter that does produce light. And it supports the formation of structure. By that, I mean it supports forming galaxies and galaxy clusters because we do find a lot of dark matter in galaxies and in galaxy clusters. So these are sort of the things we know about dark matter that the particle physicists are working with to try and find what it actually is. So one of the big debates in this is warm versus cold dark matter. So warm dark matter is dark matter particles that are fast. They're moving at like 10% the speed of light. The way that this has been studied typically is through simulations. So you have a simulation that takes some type of particle, a warm dark matter particle, and it evolves the universe over time until the present day using that type of dark matter particle. And we try to compare what we see with our observations and those simulations. So warm dark matter shows not too much small scale structure because these particles are moving really fast, so they can escape the gravitational pull of each other. So you see here, this is like a mock of the universe. These bright spots here are, oh, you can't see my mouse. The bright spots are galaxy clusters, knots, where there's lots of galaxies. And there's these filamentary structures here, and then there's these huge empty regions. So we've done the same with cold dark matter, where these particles are moving a lot slower, so they can't escape the gravitational pull of each other. And these simulations, we've seen a lot more small scale structure. So you still see those big clusters and big filaments, but those big empty regions are a lot smaller. There's still holes there, but they're not as big as with the warm dark matter. So then what we do is compare this to what we actually see in the universe. So here's an image of the cosmic web from the Dark Energy Spectroscopic Instrument, or DESI. So each of the points in the slice here, the white points, that's a galaxy. So you can see a lot of this fine structure here in this image. So DESI is taking data for tens of millions of galaxies. It's a 5-year survey, and I think we're in year 3 right now. And already you can see this cosmic web in the universe. And you still see all of those empty regions. So if we compare that to the 2 simulations, this matches up a lot better with cold dark matter. So we've essentially ruled out any particles that can move close to the speed of light as candidates for dark matter. So here are a couple more dark matter candidates. I wanted to talk about my favorite ones that I've learned about. There's a picture on the right of a bunch of different ones. I'm not familiar with most of them. That's for the particle physicists. So I wanted to talk about massive compact halo objects, or MACHOs, weakly interacting massive particles, or WIMPs, and alternate gravity. So I'll start with the MACHOs. So these are particles, but what they really are objects that are in our galaxy's dark matter halo that are the size of stars. So maybe something like this. At some point, people asked, are they brown dwarfs? Because brown dwarfs we don't see in optical, but we do see brown dwarfs in the infrared. And when we've done infrared observations, there's not enough brown dwarfs to be what dark matter is, essentially. The other case against MACHO is the Large and Small Magellanic Clouds. So these are 2 dwarf galaxies that are in our halo. And if they're traveling through our halo, so if they're passing behind these MACHOs, we should see the effects of lensing, like we saw with the clusters in the galaxies. But we've been looking at them for years and we haven't seen this effect. So we've pretty much ruled out this as a candidate for a dark matter particle. So next is weakly interacting massive particles. They did name this to contradict machos, so they picked this on purpose to be WIMPs. These are particles that are predicted to be about 100 times the mass of a proton. So they interact through gravity, and they maybe also interact through the weak nuclear force. This is a vague description on purpose because we can't be more specific about what this is because we haven't seen it. There are direct detection experiments happening. The Large Hadron Collider has been trying to produce WIMPs. And we expect that if WIMPs are dark matter particles, then they're constantly going through the Earth. They should be interacting with the atoms on Earth, and we should be able to measure that, but we haven't been able to do that yet. So WIMPs were really in style in the 2000s, and they've kind of fallen out of style a little bit. They're still my favorite candidate. This is the theory that I personally believe. But yeah. So the last thing I wanted to mention is alternate gravity. So this is the idea that dark matter doesn't exist, and we just don't understand gravity that well. So the most prominent theory in this branch is modified Newtonian dynamics, or MOND. And this was a theory created in the 80s to actually explain the flat rotation curves of galaxies. So that's directly baked into this theory. So here I have our understanding of gravity from Newton's laws, where I have the square term on the velocity. What MOND says is instead it goes to as velocity to the fourth power. And when you do this, all of the stars and the gas in the galaxy are enough to produce a flat rotation curve. So the problem with MOND is it explains these rotation curves because it starts by assuming the rotation curves are only due to stars and gas. But then when you apply this on larger scales, so to clusters and with gravitational lensing, this equation doesn't hold true anymore. So while this is a good theory that might explain things on the scales of galaxies, it's not sufficient to explain gravity as a whole. So what's next in studying dark matter? There's the DESI survey, which I mentioned earlier that I'm a member of. This is measuring tens of millions of galaxies over a 5-year period. I'm hoping that with the full 5-year data set, we're going to have way more gravitational lenses to play with and understand the distribution of dark matter, going from hundreds of lenses to thousands with this survey. Right now, with the rotation curve study of dark matter, my study is the largest sample that's been used so far at 5,500 galaxies. With DESI, we have the potential to maybe add 10,000 to 20,000 more galaxies to that study. So this gives us a lot of great statistical power. I can start looking at if dark matter is different in galaxies that are in really dense regions of the universe or really underdense regions of the universe and things like that. And then on the other side, I'm really hoping that the particle physicists figure out what dark matter actually is so that we have maybe a way to directly detect it in space. That's sort of the big dream, hopefully before I finish my PhD. The sooner the better. So just a quick recap of what I've talked about. How do we see what cannot be seen? Primarily through the effects of gravity. Right now, we primarily use these galaxy rotation curves and gravitational lensing to understand where dark matter is in the universe. And I really hope that we figure out what it is and it makes our job a lot easier soon. Thank you. Can take any question. Yeah.
Are there cold neutrinos?
So I'm not a particle physicist, but neutrinos are fast-moving particles. So they move close to the speed of light. So that's they are warm particles by nature. So that's why at least I ruled them out as a dark matter particle candidate.
Under the magnitude graphs. Normally you see, like what is the sun, the moon, there's, the numbers are positive, very high. And normally as you go far negative, they become fainter and fainter. On your chart, it showed like -13 was faint, -22 was much brighter. I'm just trying to understand that, how that.
Oh, the scale. So this is absolute magnitude. So what this does is it takes any object and it places it at 10 parsecs, and whatever the magnitude would be there, that's the magnitude in there.
Actually, no, okay,
Do you find consistent ratio between visible matter and dark matter in different galaxies, or does it vary galaxy?
So it varies. So actually, let me go back to here. So each of these points is the median in a bin, and the error bars sort of show you the spread. So I would look at the cyan points. That's where we have the most data. So to me, it looks like it definitely depends on how bright the galaxy is. So that's one part. And then within each bin, I think there's a fairly small spread. So I would say for a given brightness, I find about the same dark matter in every galaxy. But it is dependent on how bright the galaxy is.
Do we have any hypotheses on why what is changing? If the brightness is caused by the evolution of the galaxy, what's interacting with the dark matter as it evolves?
That's a great question. That's like exactly what I'm stumped on right now. There are theories that each galaxy lives inside a halo, and that there are processes that can kind of kick the gas out of these halos, so then it can't form into stars. Your total visible mass is smaller. There's also theories that your halo size has a limit on how much mass it can collect, like how much visible mass it can collect. And that depends on the size of the halo as well. So for the smaller halos, which are going to be your fainter galaxies, maybe they have a smaller capacity to hold mass. And that's why you end up seeing this downward trend. There's lots of different theories. I'm looking into it right now. So maybe in a year, I will have a good answer for you. Yeah.
I will ask it for him. So on Zoom, is it possible there are estimates for percentage of mass in a galaxy due to heavier elements could be very wrong? If so, could that account for dark matter?
Yes. I would say actually the heavier elements and the gas is probably the more well-constrained part of this. Gas is pretty easy to directly measure. And with the heavier elements, there's lots of different methods where you can you're using basically how elements combine and how they transition and how they form. And all of that goes into the estimate. So I trust those more. The more unreliable part of this, interestingly enough, is the stellar mass. Because the way we estimate stellar mass in other galaxies, we can't just count up the stars like we can in our solar neighborhood. The problem with that is we have to model how different populations look in the spectra, how stars evolve. We have to assume some sort of distribution of masses in the stars. So if anything, I would say there's more uncertainty in this contribution of stars in these galaxies. Yeah.
So I would see that the heavy metals are insignificant. But you mentioned brown dwarfs. Like, what is the percentage of mass of dwarfs? Is it more massive than the heavy metals?
That's a great question. I don't know off the top of my head. With the stellar mass distribution there, there's a percentage of mass that is considered brown dwarf mass that goes into that. So they are considered in the stellar mass.
So that's part of this.
Yes. Or it should be. There's a question of how well are we counting those as well?
Do you know the percentage of? You said it was the no visible light, the infrared.
Yeah,
Do you have an estimate of the nominal mass?
I don't. I could look into it and let you know later.
I'm just curious.
Yeah, that's more, that's all, the brown dwarf work is mostly studies in the Milky Way. So I'm honestly not an expert.
It was recently discovered that black hole and others around it, smaller mass black holes. Can they be part of the equation too?
That's a good question. So when we do this mass estimate using the total mass, the rotation in that galaxy is also due to all of that central mass. So if every galaxy has a supermassive black hole at its center, if there's more than one black hole, if it's a larger mass, that should still show up in the rotation. So it should be taken care of in that.
Got a question on Zoom from Jeff here. Does the accuracy of CO as a proxy for H2 depend on local conditions such as extreme temperature, pressure, or magnetism?
Yes, it does. So if you're looking at very small parts of the galaxy, then your conversion from CO to H2 is going to change essentially. But the surveys that we use global measurements. So you take an average, you have an average estimate of temperature and pressure when you do that conversion.
This may be ridiculous, but is there an MC squared?
No, so dark energy was named dark energy to match dark matter because it was a component we didn't understand that kind of seemed like an energy. So that's why they call it dark energy. There's no conversion in that way. Dark energy? Dark energy's, I'm totally on board with dark energy. It explains the expansion of the universe.
More mass. It's more. I've seen estimates where the dark energy is much larger component of the universe than dark energy.
Yeah, dark energy is like 68% of the universe. So it is the biggest component of the universe.
It has units of force.
Yes. So it really, the way my advisor explains this to me is that dark energy acts like a negative pressure. I didn't understand it that well either, so.
What I heard is they didn't want to call it dark force because of Star Wars.
Yeah.
That makes sense. Yes.
Is there any reason why it can't be a combination of things?
Oh,
Rule it out that it can only be one thing.
it could be a combination of things. So as the particle physicists are detecting new particles, the next thing we do is try to figure out how much of that particle makes up the mass in the universe. And then we say, this doesn't really make a dent in the dark matter budget, or maybe this does contribute. But so far, we haven't found anything that explains it, except for like the gas that I'm adding into this study. That is the one missing thing that we haven't considered before. Yeah.
Where does that 100 times the mass of a proton?
That's a great question. And that's a question for the particle physicist.
Because that seems like a complete guess, because could you have 50
So
times that were, there are twice as many of them?
in the standard model, there's this like supersymmetry. So if you buy into the supersymmetry, I believe this particle is predicted by it, and that particle has a mass of about 100 times a proton. But I'm not a particle physicist. Yes.
Is the density of galaxies like pretty uniform?
No, it's not uniform at all. So
And the total there's visible density and total density, and neither are very consistent or?
No. So the majority of the universe, we think, is empty space. So there's no galaxies. But the majority of galaxies live in these clusters and filaments. Based on our simulations, so essentially dark matter is the thing that in the early universe started coming together first, and then it pulled all of this gas together. So these largest sort of dark matter halos are in the most dense parts of the universe, but there's also dark matter in the empty parts. It's just not enough to pull in the gas, and all of that gas has gone to the walls already. So it's not uniform. That's what we call it, the cosmic web.
Is there any research that you know looking at other types of galaxies, like elliptical galaxies? They showed similar characteristics in terms of dark matter and spiral galaxies.
I do know other research on that because that's what I'm doing now. I'm studying elliptical galaxies. The problem with elliptical galaxies is they don't have organized motion, so you can't directly probe the mass from their velocity. With elliptical galaxies, you have to use the virial theorem, like Fritz Zwicky did, where you measure the random motion of things in the galaxy and you make a mass estimate based on that. So what I'm finding in my work is that we make a lot of assumptions, and Fritz Zwicky made a lot of assumptions along the way, and so still figuring out how to make that actual calculation. A lot of theory predicts that the ratio in elliptical galaxies should be the same as spiral galaxies, because our main theory of galaxy evolution is that elliptical galaxies form from mergers of spiral galaxies. So if they bring all the dark matter with them, that ratio should stay the same.
We've got another question online. Are there any other techniques besides gravitational lensing for teasing out information about dark matter structure and distribution?
Not that I know of for anything outside of our galaxy. So the lensing is the main one right now. Other than simulations, where you're sort of performing a simulation, trying to compare it to what you see.
From the halo effect that you had in some of the diagrams, it appears that if you follow that, it appears that the concentration of dark matter is not uniform.
No. So
Really thin, spread out, and the farther away you are from that galaxy clusters, less and less dark matter.
yes.
Fixed.
So the leading theory for the distribution of a dark matter halo is a very strong cusp in the center, so a very dense center, and there's less and less as you get away. It falls off exponentially as you get away from the center of any halo.
So in all our lifetimes, I've heard the term, he's talked about a lot of theories, but I've heard the term the existence of dark matter is proven. And what does that mean?
So I personally would never say, at this point, I wouldn't say the existence of dark matter is proven. At least
people think those.
Yeah, I don't think that's a fair claim to make, because we're studying the gravitational effects of something right now. And Mond is actually coming back into style right now in the last like 5 years or so. Everybody's kind of into modified gravity again. So I would say I wouldn't feel comfortable making that claim until a particle is discovered. But I really do hope it exists, because otherwise I'm out of a job.
But it's needed for expansion.
It is needed for expansion if the theory of general relativity is correct, which I think is pretty much, that's set. We don't need to think about that anymore. But, we're at the point in dark matter studies where now we've been doing this almost 100 years. And for rotation curves, we've been doing this for 40 years. And we're starting to get antsy about the fact that we haven't found the thing yet. So we expected to find it in the 2010s. And then when we didn't, everybody lost hope, and modified gravity theory started coming back.
Do you ever take James Webb data and throw it into your models?
So James Webb, because it's largely photometry, it's not as useful for me. It's all it doesn't have the resolution that I need. So these maps of galaxies, they're very observationally expensive. They take a lot of time. So there's very few dedicated studies for that. So we have manga here. There's a SAMI, which is in Australia, that also does similar stuff, but they've had a 3-year survey and they've only done 300 galaxies. So I don't have a lot of data I can use for this. That's why I'm hoping with DESI I get to expand to like 20,000 galaxies. Yeah, James Webb unfortunately doesn't give me the information I need.
Any evidence to support the idea that dark matter could be just dust?
It would have to be a lot of dust, and the question then becomes what stars are producing this dust? Where is all of this dust coming from? Yeah, dust is like it's reflective and we can observe it, and it also emits in infrared, so
Question on Zoom. The picture that is on the screen now showing Desi's imaging scope as an inset shows colored arcs to the left. Do the colors mean anything other than the deeper and deeper insights?
yes. So the colors are actually different surveys within DESI. So the closest arc is the Bright Galaxy survey. So those are all of the galaxies closest to us. I forget the redshift limits. Past that is the luminous red galaxies. Then there's a focus on quasars in the next set, and then past that is emission line galaxies. So it's what galaxies we're able to observe easily in that distance range. Yes.
That ring pattern you showed earlier of a galaxy, is that common of all the galaxies or not this one?
Oh, the Einstein ring. I forgot where I put it in.
No, not this one.
Oh, this?
Yes.
I think the study has only been done on this galaxy cluster, so I couldn't tell you. This is not what, based on theory, that's not what I expect to see.
What would you expect?
I would expect to see a lot of blue in the center that just sort of falls away as you get further off. So kind of like what you already see in the inside the ring part. Just that. I have no idea why there's a ring in this one. It's very interesting.
It's like it's almost being repelled by gravity.
Yeah, that would be
a ring.
that would be interesting. Yeah, that's a good point. I wouldn't expect to see like an effect that large from something like that because I assume they would have done multiple like tested multiple models on this, and I'm very surprised by the existence of the ring. But all of this should be geometry essentially, so it should be straightforward to find this distribution.
Could you say again how the currently displayed image was created?
So the left side is the actual observed cluster, and there's lots of images from the lensed galaxies behind this cluster. And the lensed images were used to backtrack what the mass distribution of this cluster should be to produce those images.
Sorry, I got so many questions. Is there so do you measure the dark matter in very deep space, or do you just measure it close to About close to us.
Close is a very relative term in astronomy. So all of my data is from outside of our galaxy. It's within redshift of 0.03, which is a very close universe. It's 400 million light years. With DESI, when I expand into that, I'm going to triple the distance, more than triple the distance that I'm reaching, which is still considered the local universe in that study. So it really
that would be-
depends.
So beyond the local universe has been estimated.
Has there been estimates beyond the local universe? Not directly, only through simulations. One of the things that has been proposed for studying the dark matter distribution far away is using weak lensing. So instead of strong lensing where you see all these images, weak lensing, you would really only see the effects of the mass bending the light in spectra. So the idea is you take something really far away, and on its way to us, the light is passing lots of gravity sources. And some of those are galaxies, but maybe some of those are voids and empty spaces. And that light is going to be bent a bunch of times before it reaches us by all of the dark matter that's between us and that galaxy. So the idea is maybe we could retrace or backtrack where the dark matter is along that line using that light. But it's a very complicated process, and there's you would end up definitely with more than one possible distribution of dark matter.
Thank you.
Yes, thank you. I was really good. Enjoyed that. If anyone would like a shirt, let us know. They're downstairs. If anyone, I don't think we're gonna be able to observe. Bob said there's rain coming, it looks like. Yeah. Yeah, it's raining hard, so be careful when you depart. And